Hey guys, so I just wanted to keep you caught up on what we're doing in class. So today we started working on the lab 2.1, which is the introduction to thermal energy. So yesterday, hopefully you saw my video and were able to complete the forms of energy activity. And the point of that was we know that there's really six main types of energy, and that energy isn't created or destroyed, it's transferred, right? So we transfer energy from one form to another. That's actually the first law of thermodynamics. So that's something we need to add to our notes. So again, first law of thermodynamics is energy is not created or destroyed, it's transferred. Okay, so if you need to pause the video and write that down, that's fine. So now, jumping into the lab, um, we're looking at thermal energy. Okay, so we're looking at really heat and what heat is. So our first question is, does heat have mass? Okay, that is going to kind of be our driving question on what we want to do in part one. So just like normal, go ahead, if you need to pause the video if you haven't done this, you're going to fill out this lab in your notebooks just like normal. Okay, so you're going to go through, you're going to write your purpose statements, your hypothesis, we're going to write in just a second. I want to talk a little bit about it. And then our data table. Okay. So let's look at our hypothesis first. So basically what we're going to do, or what we did in this lab, is we had a little chunk of metal. And we took that metal and we got the mass of it before we heated it up. Okay, so it was the cold mass. Then we took that piece of metal and we put it into a beaker and used hot water to heat up the metal or add heat to the metal. So what I want you guys to do now is write a hypothesis that basically says, okay, does heating up the metal, is that going to affect the mass? So if you think yes, it will, what we're saying is then that heat has some sort of mass, right? Because that's the only thing that we're adding to the metal. So your hypothesis would be something like, okay, if we add heat to the metal, then the mass will change, or then the mass will increase. Okay. If you don't think it's going to change, then you're saying, okay, heat does not have mass. Okay, and that hypothesis would sound something like, okay, if we heat up the metal, then the mass will remain the same. Okay, so pause the video, write your hypothesis real quick. Okay, now here's our data. This is what we found. Okay, so we're going to copy this into our notebooks just like we were here. Okay, so when we took the mass of the cold metal, it was about 23.5 grams, heated up to really, really hot, and it was still 23.5 grams. Okay, so why is that? Okay, and what the answer really is we find that energy is massless. Okay, and energy is really a way of describing what's happening to our material, right? Because heat is a result of atoms moving. Okay, so if they're moving really, really quickly and colliding, that's going to transfer that into thermal energy. So it heats up. So really, heat is explaining the movement of those molecules. Okay. Same thing with our other forms of energy, like nuclear energy is the fusing or the breaking of the nucleus of the atom. Okay, and it releases a large amount of energy. So energy in itself isn't a thing. It's a way of describing what's happening to our materials. Okay, so it doesn't have mass. So our answer to our analysis question should be no. Heat does not have mass. What is our evidence? Our evidence is that the metal had the same mass before and after we heated it up, right? And then the last piece is then just connect if you think your hypothesis was supported or not. Okay. So go ahead and pause the video and write your analysis portion. Okay. Now the next part of the lab, part two, nice, is we want to know do all metals or all materials conduct energy the same? So what we did is we had 5 different types of metals, okay, and we had them in boiling water, which is, we know, should be right around 100 degrees Celsius. It's a little bit lower than that here. And then we took them out and we put them on an ice block, okay, and obviously they're going to transfer that heat or that energy to the ice. And when we do that, the ice melts and they start to sink down. Let me see if you can see my finger. There we go. They start to sink down into that ice block. So the idea was the better they are at conducting heat, the further they're going to travel into that ice block, which is kind of cool. Okay. And so what we did is this relative depth is we ranked them. Number one means they were the best conductor or they went furthest into the ice. Number five means they were the worst conductor, okay, and they didn't transfer their energy very well, okay. And we'll look more on that when we talk to like specific heat, things like that. So we found this makes sense, right? Copper is a very, very good conductor of electrical energy, but it's also a good conductor of thermal energy. So we see copper in all sorts of things like heat exchangers, copper wires, those things, because it's such a good conductor. Then things like lead, it's not as good of a conductor. Its structural makeup doesn't allow it to conduct electricity or conduct heat as well. Okay, so that's what we found with part 2 of the lab. Now it asks you to create a graph representing the relative depths. Okay, so now this is kind of tricky because what we want those graphs to do is show us. They want to be a visual aid, right, to help us understand the information better. So on our x-axis or our vertical, or sorry, our y-axis, our vertical axis is going to be the relative depth, right? Which one went the furthest? Which one went the shallowest into the ice? And then on the y or on the x-axis, sorry, on the x-axis is going to be our type of metal. So what we want to make sure is, however you set that up, we want that graph to show us that yes, this is the best conductor, right? So usually that means like the biggest. So try and think about a way to do that, right? So if this is the best conductor, how are you going to show that? And create that graph. Okay. And then when we look at the question, it says, okay, which metal transferred its heat into the ice best? Obviously, that's going to be copper, right? It transferred that energy into the ice, which caused it to melt more, which causes it to drop down further in the ice. Which one was worst? Lead, right? It held on to that heat, so it didn't transfer that into the ice block. Therefore, it's not going to melt as much. Okay, so that's parts 1 and parts 2. So part 3 tomorrow. We're going to talk about calculating heat. So I'm just gonna send you this for now to have this work for you guys to work on now. And then tomorrow we're gonna do parts 3 and part 4. And I'll send you guys another video. Okay. Let me know if you have any questions. Big thing is just go through it, use the video, use the results from the video to complete the lab in your notebook just like we normally would. Okay. All right, guys. I hope you're doing okay. Talk to you soon.